Here is section 5.4, exercise 106. It's an interesting one. We just want an antiderivative, and we have e to the 2x plus 2e to the x plus 1 all over e to the x. This is sort of interesting in a couple of ways. One is not that I think it would really get me anywhere, but noticing the e to the 2x and then the 2e to the x and the plus 1. Well, e to the 2x, oops, no, I can't write it up there. E to the 2x, remember that that's e to the x squared. And so that top is actually a perfect square. So the top appears to be e to the x plus 1 quantity squared. But actually, I don't think that really gets me anywhere because, I'd maybe try to make a substitution of e to the x, and I've got that e to the x on the bottom, or e to the minus x, and so I don't think that does me much. But on the other hand, if I simply divide through all of this by that e to the x, I have an e to the x, because that's e to the 2x divided by e to the x, so that's e to the 2x minus x. So I get that one, and then plus 2, and then plus 1 over e to the x, but that's just e to the minus x dx. And so I know this first part, the antiderivative of e to the x is just e to the x. The antiderivative of 2 is just 2x. And then now the antiderivative of e to the minus x is just minus e to the minus x. We could go ahead and do that more formally. But it's one of these things that if I do it enough, I kind of start remembering. So if I let u equal minus x, then du is minus dx. And so I just need to put a minus here and a minus there. And so this is e to the x plus 2x, minus the antiderivative of e to the u du. And so that's e to the x plus 2x minus e to the u plus an arbitrary constant, which is e to the x plus 2x minus e to the minus x plus an arbitrary constant. And notice, I could have put an arbitrary constant up here, but I still had that antiderivative sign, so I didn't worry about the constant until I got rid of all antiderivative signs. And there we go. That is 106.